Calculus 6, Real Analysis, Sequences and Convergence. Definition of a sequence. A sequence is an ordered list of real numbers arranged according to a rule, according to a pattern. There's a pattern within the arrangement, within the sequence. The sequence assigns to each natural number n within the natural numbers pool or n space a real number an, also referred to as the nth term of the sequence. The sequence is written as a of n from n equal 1 to infinity equal a1, a2, a3 all the way to a infinity, to very large numbers. As an example, an equal 1 divided by n, which gives us 1 divided by 1, 1/2, 1/3, 1/4, 1 divided by 5, all the way to 1 divided by n, where n is a very large number. Capital N, if I should be more precise. And it goes to 1 divided by infinity, which, by the way, when you divide by a very large number, you end up with 0. That would be the concept of a limit in such case. Now, concerning the pattern that I've talked about, okay, for instance, for an equal 1 divided by n, progressively, you notice something that as n increases, you keep dividing by a larger number. And that number increases sequentially. This is actually why we call it a sequence. So 1 divided by n, for n going from 1 to 2 to 3 to 4, becomes 1 divided by 1, which is 1, then 1/2, then 1 divided by 3. The denominator keeps increasing sequentially and keeps being incremented by 1. But the numerator is stable. However, you keep dividing by a larger number. As this number grows, there's a pattern, there's a specific orientation for that sequence. Either it is increasing by value or it is decreasing. Obviously, here in this case, it is decreasing all the way to get to 0. Let's talk right now about the types of sequences. So, at first, you have the constant sequences. For a constant sequence, all terms are equal. As an example, an equal 5, regardless of the value of n. Because as you notice, there's no n variable within this statement. So an never changes. It remains constant at 5, or it can be rewritten as an equal 5 for all natural numbers. Of course, n greater than or equal to 1. It's like the height of water within a pool. It doesn't matter from which location you are measuring the height of water. If you have a flat bottom, of course, the height value always remains the same. Monotonic sequences. Monotonic means it's either increasing or decreasing, meaning that the follow-up terms, as the index grows, the sequence is either growing in value or decreasing in value. So for the increasing, for instance, an plus 1 is greater than or equal to an. It means that as n progresses, the subsequent terms are greater than the previous terms or equal. So for some locations within the sequence, it might plateau, it might be stabilized at a specific value for 2 or 3 terms, for example, then it keeps growing up. But in average, it's growing, it's increasing. Strictly increasing means that each term is strictly greater than its previous term. So an plus 1 is greater than an. Same thing for decreasing, monotonic. Decreasing as an plus 1 less than or equal to an. So for some values or for some indexes, you have equal values between the forward or the previous, but for others, it decreases. But in average, the sequence is declining, is decaying, in other words. Strictly decreasing means that an plus 1 is always less than an. So the subsequent values are always less than the previous values, like 1 over n that we've seen previously. Bounded sequences. You have 3 types here, either bounded above or bounded below or bounded both. Bounded above is that there exists a number, natural, actually real number, capital M, within the R space, such that an is always less than or equal to capital M for all values of n. Now, an may not necessarily achieve m literally. Okay, it may approach to m if m is simply an upper limit. So m is the upper boundary that an can never cross, can never go beyond. Now, for the bounded below, an is always greater than or equal to m, a minimum value, a minimum number. So it means that for all values of n, an is always greater than or equal to lowercase m, which is the lower bound, the minimum value that can be had by the sequence. Now, if it's both bounded from above and below, then it is bounded in general, which is a very important premise. Convergent sequence. This convergent sequence, it means that the sequence approaches a finite limit, as n approaches infinity, of course. And another thing to point at is that if a sequence is both monotonic and bounded, it means that the sequence is convergent as well. Limits are so important because they help us evaluate the limit of a function and understand its behavior at infinity, whether it converges to a finite value or it diverges, meaning that it either blows up to infinity or it keeps swinging between 2 or 3 values, so it never fixates on one finite value, but it keeps oscillating, like sine x, for example, is a divergent function. Continuity, differentiability, and integration rely on the analysis of sequences, so that's why they are very important. Limit of a sequence. So let an be a sequence of real or complex numbers. The sequence an has a limit L designated as limit as n approaches infinity of an equal L. If the terms of the sequence get arbitrarily close to L as n approaches infinity or becomes very large. So if as n approaches infinity, the terms themselves of the sequence get arbitrarily close to L, to the limit, then this is what is called the limit of the sequence. Okay, get arbitrarily close to the value of L, so L becomes the limit of that sequence as n becomes very large or as n approaches infinity. Epsilon-N definition. So limit of an as n approaches infinity is equal to L means that for whatever epsilon value, epsilon being a very infinitesimal small number, very close to 0 by the way, for whatever epsilon greater than 0, there exists a number n within or among the natural numbers such that for all n greater than or equal to capital N, which is a very large number in the natural numbers, an minus L is less than epsilon. In other words, the difference between the sequence and the limit itself as n approaches a very large number, that gap between these two becomes very small and approaching epsilon, which is a very small gap. As n approaches a very large value, to put it more simply and plainly, an approaches the limit in such a way that the gap or the difference between an, the sequence, at that value, capital N, and the limit itself becomes very small and approaching epsilon. So no matter how small a distance epsilon greater than 0 you choose, there exists an index n such that for all n greater than or equal to capital N, the distance between an and L is less than epsilon. In simpler terms, the sequence approaches L, the limit, with a very tiny infinitesimal gap of epsilon, such that an minus L in absolute value is less than epsilon for epsilon greater than 0, as n becomes very large, of course. Now, the series converges when it has a limit, so they go hand in hand together. Examples of sequences. First, converging sequence. That would be like the examples that we've seen before, which is an equal 1 divided by n, for which as n, the value of n increases, the value of an decreases, okay, because you start dividing by a much larger number. So we say that an decays all the way to 0, because the limit of an as n approaches infinity is equal to 0. Second example, constant sequence, that would be like an equal 8. So it doesn't matter what the value of n is, an, in our case here, is independent of n. There's no n variable within the sequence an. So an remains the same value. It remains constant for all values of n. So limit an when n approaches infinity is equal to 8. Diverging sequence, an is equal to n, for example. So as n increases, an normally increases in the same manner. Why? Because an is equal to n. So limit an as n approaches infinity is equal to infinity. It blows up, we say. And in other words, it doesn't have a finite limit. It doesn't have an upper bound. It never reaches a finite value. Characteristics of a sequence. A sequence has a limit if and only if it converges, meaning that the two go hand in hand together. So it cannot converge if it doesn't have a limit. And by the way, the limit also needs to be finite for it to converge. If the sequence does not approach a finite number when n approaches infinity, then it diverges, which means it doesn't approach any value. It keeps meteorizing, either in the case of oscillating divergence, meaning that it keeps swinging between 2 or 3 or different values within an interval, or it keeps growing to infinity. Every convergent sequence is bounded, but the inverse of that is not necessarily correct, meaning that we can have a sequence bounded by an interval of values, but the sequence itself keeps jumping between these two values, so it never achieves a definite limit, a final limit. So the limit does not exist, despite the fact that we have bounds, and the sequence never converges. Convergent and divergent sequences. Convergent sequence. A sequence an is convergent if it approaches a real number L as n approaches infinity, and it should be a finite number. Meaning that as n grows very large, the sequence gets closer to L, which is the limit of the sequence when n goes to infinity. So limit of an as n approaches infinity equal L means that for all epsilon greater than 0, there exists a number n within the natural numbers, such that for all values of n greater than or equal to capital N, that big number, an minus L minus the limit is less than epsilon. As an example, an equal 1 divided by n. Hence, limit of an as n approaches infinity is equal to 1 divided by infinity equals 0. Divergent sequence. A sequence diverges if it does not converge to any finite number. There are mainly two types of divergent sequences. Infinite divergence, the terms in which grow without bound. Example, an is equal to n squared, so limit of an as n approaches infinity is equal to infinity. And with a square value, so it approaches infinity even faster than n itself. Oscillating divergence, the sequence keeps swaying between two or more values and never settles on a finite fixed one. Example, an equal minus 1 to the power of n. As n approaches infinity, an keeps swinging or jumping back and forth between minus 1 and plus 1. So the limit does not exist, and hence the sequence diverges. Bounded and monotonic sequences. A sequence an is bounded if its terms stay within a fixed range. Bounded above, there exists a real number capital M such that an is less than or equal to capital M for all values of n greater than or equal to 0, which means that an can never go beyond the value of capital M. That's the highest bound. That's the highest value that can be achieved by an. Bounded below, there exists a real number lowercase m such that an is always greater than or equal to lowercase m for all values of n greater than or equal to 0. Usually the sequences start from n equal 1. So no matter what n would be, an is always greater than or equal to m. So this would be the lower bound. Bounded sequence. A sequence is bounded if it's bounded both from above and below. In other words, there exist real numbers lowercase m and uppercase m such that an is greater than or equal to lowercase m, less than or equal to uppercase m for all values of n. So an keeps changing or varying between these two lower and upper bounds. It never crosses down or up between these two. As an example, minus 1 to the power of n is bounded between minus 1 and plus 1, despite the fact that it has no limit as we mentioned previously. Monotonic sequences. A sequence is monotonic if it's either always increasing or always decreasing. If it's monotonic increasing, then an plus 1 is greater than or equal to an for all values of n greater than 0. In other words, all the subsequent terms for the sequence an are greater than the previous terms. For each term that comes after a term before it, this term is greater than the term trailing behind that specific term. Okay, so for whatever an plus 1 or the value of a term at n plus 1 index is greater than the value of the term right behind it at index n. Now, strictly increasing means that there are no plateaus. There are no values for which an plus 1 is equal to an. It's always strictly increasing. Meanwhile, for the upper increasing example, where you have an plus 1 is greater than or equal to an, you might have for some values a stabilization where the values are not increasing all the time. Monotonic decreasing, an plus 1 is less than or equal to an for all values of n greater than 0. What this means is that the subsequent values of an are always decreasing in respect of their previous values. So for each term an plus 1 at index n plus 1, it is less than or equal to the term right behind it, or the value of the term trailing it. Strictly decreasing means the same thing as above, so the terms are strictly decreasing in value and there are no plateaus. There are no values that are equal for some interval of time. Theorem: a sequence that is both bounded and monotonic is then convergent. As an example, an equal 1 minus 1 divided by n. As n increases, an increases. It is bounded by 1 from above as it converges to 1. This is as n approaches infinity, the second component, 1 divided by n, becomes 0. That's why the upper bound is 1. At the same time, for n equal 1, you have an equal 1 minus 1, which is 0. That would be the lower bound. Exercise: find the limit and check the convergence for the following sequence: an equal minus 1 to the power of n divided by n. Let's check the limit at first. For the numerator, minus 1 to the power of n, as n goes to infinity, it keeps flip-flopping or jumping between minus 1 for odd n values and plus 1 for even values. So it diverges. It never reaches a finite limit. However, when divided by the denominator, which increases as n increases, the sequence approaches 0. So the jumping of sign does no longer matter. So this happens for very large n values. Hence, limit of an as n approaches infinity is equal to limit of minus 1 to the power of infinity divided by infinity equal 0. Checking if an is bounded. As mentioned before, minus 1 to the power of n gives us minus 1 for odd values of n and plus 1 for even values. So for n odd, you have minus 1 divided by n less than 0, and for n even, plus 1 divided by n is greater than 0. Now let's prove the upper bound. We look for a number m, capital M, such that an is less than or equal to m for all values of n. Since the largest value occurs at a2 equal 1/2, because that's the first time when n becomes even and renders the numerator positive, and all other terms are smaller, so we can take capital M is equal to 1 divided by 2. So an is less than or equal to 1/2 for all values of n. Hence, the sequence is bounded from above or bounded above by value m equal 1 divided by 2. Let's now prove the lower bound. So we look for a number lowercase m such that an is greater than or equal to m for all values of n. The smallest value occurs at a1 equal minus 1. So for n is equal to 1. And all the other values approach 0. So the lowest value that you can get is an is equal to -1. Hence, an is greater than or equal to -1 for all values of n. So the sequence is bounded below by an equal -1. Again, to remind you as to why an approaches 0 as n increases, because you are dividing by n. So as the denominator's value increases, you are dividing by a larger and larger number. This makes the entire sequence decay all the way down to 0. And by the way, 0 happens to be greater than -1. That's why -1 is the lower bound, not 0. The sequence is bounded above by +1 divided by 2 and below by -1, so it is bounded. You have an is greater than or equal to -1 over n, less than equal to +1 over n. So an is greater than equal to -1, less than equal to +1/2, which are respectively the lower and upper bounds. Checking monotonicity. If an is increasingly or decreasingly monotonic. So let's try some few terms. a1 is equal to -1, a2 equal 1 divided by 2, a3 equal -1 divided by 3, a4 is equal 1 divided by 4. The sequence keeps decreasing then increasing, meteorizing or swapping between positive and negative values, so it is not monotonic. The limit exists, however. Limit of an as n approaches infinity is equal to 0, so the sequence converges despite the fact that it keeps going up and down, keeps increasing and decreasing, and it ain't monotonic. Now let's prove the convergence. Let epsilon be greater than 0. There exists a number, capital N, very large, greater than 0, such that an minus L is less than epsilon whenever n is greater than or equal to capital N. So you simply place an minus L less than epsilon. The limit is 0, -1 to the power of n divided by n, minus 0, an absolute value. Remember, so -1 becomes +1 divided by n is less than epsilon. Hence, n should be chosen equal to 1 divided by epsilon. Let's reevaluate the limit based on this premise, which is n equal 1 over epsilon. So limit of an as n approaches capital N is equal to -1 to the power of n divided by n equal -1 to the power of 1 over epsilon divided by 1 over epsilon. Now you switch epsilon back to the numerator. It is inverted twice. It is the inverse of the inverse. It gives you back the numerator, which is equal to epsilon multiplied by -1 to the power of 1 over epsilon, which is infinity, by the way, because epsilon is very close to 0. However, this term that keeps flapping between -1 and +1 is multiplied by epsilon, which is again a very small number, very close to 0. So it counts as 0, hence the limit is equal to 0. Epsilon, again, is a very small number close to 0, so -1 to the power of 1 divided by epsilon, despite the fact that it goes to infinity and keeps flipping between -1 and +1, it is multiplied by an infinitesimal number close to 0, so the limit is 0, which verifies the convergence. Exercise. For the following sequence an equal n divided by n plus 1, find the upper and lower bounds. Is it monotonic? Does an converge? And find the limit if it does, and prove the convergence. Upper bound. Considering n within 1, 2, 3, all the way to capital N, or the n space, or n strictly greater than 0, there exists a number, capital M, such that an is less than or equal to m for all values of n, greater than 0, of course. For n equal 1, a1 equal 1 divided by 2. Now, as n keeps increasing, an keeps approaching 1 because the denominator, the constant here within the denominator, becomes negligible or insignificant. So the upper bound is +1. Now, for the lower bound, there exists a number m such that an is greater than or equal to lowercase m for all values of n strictly greater than 0. Again, for n equal 1, a1 equal 1/2. That would be the lowest number because as n keeps increasing from 1/2, an keeps increasing until it reaches 1. So the lowest bound is 1 divided by 2. An is bounded above by 1, which is the suprema. An is bounded below as well by 1 divided by 2, which is the minima or infima. I don't remember exactly what they call it. So an is bounded in general in a way that an is greater than or equal to lowercase m, less than equal to capital M, or an is greater than equal to 1 divided by 2, less than or equal to plus 1. Checking monotonicity. So a1 is equal 1/2, which is around 0.5. a2 equal 2/3, 0.66. a3 equal 3 divided by 4, which is 0.75, etc. And you notice that an keeps increasing as n keeps increasing. As n increases, an keeps increasing gradually, so an is strictly increasing, but let's analytically demonstrate it. For the sequence an to be monotonic and increasing, an plus 1 should be greater than an. So we need to solve an plus 1 minus an. Let's check an plus 1 minus an. So instead of n, you replace it by n plus 1. You get n plus 1 divided by n plus 1 plus 1, which is n plus 2, minus n divided by n plus 1, which is an, equal to n plus 1 squared minus n squared minus 2n, divided by n plus 2 times n plus 1 equals 0. So n squared plus 2n plus 1 minus n squared minus 2n divided by n plus 2 times n plus 1 equal 1 divided by n plus 2 times n plus 1. And you see that it's strictly positive and strictly greater than 0. Hence, this sequence is strictly increasing or monotonically strictly increasing. Does an converge, and find the limit if it does? Since we have a fraction, we'll apply the L'Hopital rule to evaluate the limit. We multiply the numerator and the denominator by the inverse of the highest power, which is 1 divided by n. So limit of n divided by n plus 1 as n approaches infinity is equal to the limit of 1 divided by n multiplying both the numerator and the denominator as n approaches infinity equal limit of 1 divided by 1 plus 1 divided by n. 1 over n approaches 0 as n approaches infinity. So we end up with 1. Hence the limit exists and it's a finite number, so an converges. Let's prove the convergence. Let epsilon be greater than 0, epsilon an infinitesimally small number close to 0. There exists lowercase n greater than or equal to capital N, n being a very large number, such that an minus L is less than epsilon for n greater than or equal to capital N, which means that as n approaches a very large value, the difference or the gap between the sequence and the limit becomes very small. An minus L in absolute value is less than epsilon is equal to an, which is n divided by n plus 1, minus 1 in absolute value is less than epsilon. So n minus 1 divided by n plus 1 is less than epsilon, which is equal to minus 1 divided by n plus 1. Again, in absolute value, it becomes positive. So 1 divided by n plus 1 is less than epsilon. So 1 is less than n epsilon plus epsilon, which gives us n epsilon is greater than, we moved epsilon to the left. So n epsilon is greater than 1 minus epsilon. Hence, n is greater than 1 minus epsilon divided by epsilon, which is 1 divided by epsilon minus 1. So we need to choose n value is equal to 1 divided by epsilon minus 1. Now let's prove the limit or the convergence using this value by re-evaluating the limit. So let's evaluate the limit when n approaches capital N, which is equal to 1 divided by epsilon minus 1. Limit an as n approaches capital N is equal to 1 divided by epsilon minus 1 divided by 1 divided by epsilon minus 1 plus 1. And the denominator minus 1 cancels out by plus 1. So we are left with 1 minus epsilon divided by epsilon over 1 divided by epsilon. you can factor out epsilon. So what you're left with is 1 minus epsilon. Epsilon is a very small infinitesimal number close to 0 and it doesn't count. Hence the limit is equal to 1 because epsilon is regarded as 0. So an is convergent. Another one, an is equal to square root of n squared plus 3n minus n. Find the upper and lower bounds. Is it monotonic? Does an converge? And find the limit if it does and prove the convergence. You can pause the video, like all of the videos, to try to solve it yourself. Find the upper and lower bounds. At first, we need to reshape the equation in a way to fix the problem here that we have n squared and n within a square root, which are positive, and another n which is negative on the outside. Okay, so we need to multiply an by its conjugate, both the numerator and the denominator. Now you would ask, okay, but it doesn't have a denominator. Actually it does, if you can consider it as square root of n squared plus 3n minus n divided by 1. So an is equal to square root of n squared plus 3n minus n. You multiply it by square root of n squared plus 3n plus n divided by square root of n squared plus 3n plus n is equal to n squared plus 3n minus n squared divided by square root of n squared plus 3n plus n equal 3n, because n squared cancels out, divided by square root of n squared plus 3n plus n. Now, n squared can be taken out as a common factor under the square root. So you divide by n squared the components and you take n squared as a common factor, which gives you 3n divided by square root of n squared multiplied by 1 plus 3 divided by n plus n. Now n squared can be removed to the outside. It becomes n square root of 1 plus 3 divided by n plus n. We have n as a common factor in both the numerator and the denominator, which renders an equal to 3 divided by square root of 1 plus 3 divided by n plus 1. Let's check the lower bound. There exists a number m, lowercase m, such that an is greater than or equal to m for all values of n within n space. So a1 is equal to 3 divided by 1 plus 3 plus 1, which is 3 divided by square root of 4, which is 2 plus 1, 3 divided by 3 equal to 1. Now a2 is equal to 6 divided by square root of 1 plus 3 divided by 2 plus 1, which is approximately 1.16. So the sequence is increasing. As n increases, an increases from 1. So the lower bound is a1 is equal to 1. Hence, an is greater than or equal to 1 for all values of n, or all values of n within the natural space, and n being strictly greater than 0. Let's find the upper bound. So there exists a number m, capital M, such that an is less than m, less than or equal, by the way, for all n within the natural space. So as n approaches a very large value, 3 divided by n approaches 0, and an approaches 3 divided by 2. Hence, 3 divided by 2 is the upper bound. That's the maximum value that an can reach or can approach. So an less than or equal to 3 divided by 2 for all n within the natural space is the upper bound. An is bound by 3 divided by 2 from above, which is the suprema. An is bound by 1 from below, which is the minima or infima. Hence, an is bounded in general. So an is greater than or equal to lowercase m, less than or equal to uppercase m, or an is greater than or equal to 1, less than or equal to 3 divided by 2. Is it monotonic? An plus 1 is greater than or equal to an is monotonically increasing. If an plus 1 is less than or equal to an is monotonically decreasing. If it is greater, strictly greater than or less than instead, then an will be strictly increasing or decreasing respectively. Of course, monotonically. Let's check an plus 1 minus an equal 0. So square root of n plus 1 squared, we simply replace n by n plus 1, plus 3 times n plus 1 minus n plus 1 minus square root of n squared plus 3n minus n, which is an, is equal to 0. Square root of n squared plus 2n plus 1 plus 3n plus 3 minus 1. You have minus 1 here and minus n versus plus n, so n cancels out, minus square root of n squared plus 3n equals 0. Square root of n squared plus 5n plus 4 minus 1 minus square root of n squared plus 3n is equal to 0. So square root of n squared plus 5n plus 4 is equal to plus square root of n squared plus 3n plus 1, and we need to square both sides of the equation. So we elevate left and right to the square power, which gives us n squared plus 5n plus 4 equal n squared plus 3n plus 2 square root of n squared plus 3n plus 1. Now n squared cancels out, so we are left with 5n minus 3n plus 2. Actually, plus 3 is equal to 2 square root of n squared plus 3n. We need to square both sides for the second time, the left and the right of the equation. So 2n plus 3 squared is equal to 2 square root of n squared plus 3n squared, which gives us 4n squared plus 12n plus 9 equal 4n squared plus 12n. Left and right cancels out, and we are left with plus 9, which is a positive, strictly positive value, which means that this sequence is strictly increasing. So since we are left at the end with plus 9, which is a strictly positive number, so we conclude that an is monotonically strictly increasing. Does an converge? And let's find the limit if it does. Since an is bounded and increasingly monotonic, then it converges, even without going into the proof of the limit, okay? But we're gonna prove it anyway. So, and by the way, proving the limit means as well proving the convergence. Limit of an as n approaches infinity is equal to the limit of 3 divided by square root of 1 plus 3 divided by n plus 1 equals 3 divided by 2, because 1 over n, or rather 3 divided by n, approaches 0 as n approaches infinity. Another proof that an converges is that the limit exists and it is equal to 3 divided by 2, which means it is a finite number. Prove the convergence. So again, limit an as n approaches infinity is equal to 3 divided by 2. We want to prove that. Let epsilon be greater, strictly greater than 0, epsilon being a very small number. There exists capital N greater than 0, such that an minus L approaches epsilon. The gap becomes very small as n becomes very large and approaching capital N. an minus L is equal to square root of n squared plus 3n minus n minus 3 divided by 2 is less than epsilon, an absolute value of course. So square root of n squared plus 3n is less than, we moved n to the other side of the inequality along with 3 divided by 2, which was negative, so it became positive. So square root of n squared plus 3n is less than n plus epsilon plus 3 divided by 2. You square both sides, so you get n squared plus 3n is less than n plus epsilon plus 3 divided by 2 squared. N squared plus 3n is less than n plus epsilon squared plus 3 times n plus epsilon plus 9 divided by 4. So it is equal to n squared plus 2n epsilon plus epsilon squared plus 3n plus 3 epsilon plus 9 divided by 4. N squared cancels out, 3n as well. We are left with 0 less than 8n epsilon plus 4 epsilon squared plus 12 epsilon plus 9. So n less than 4 epsilon squared plus 12 epsilon plus 9 divided by minus 8 epsilon. We multiply the other side with minus while flipping the inequality to greater than. So lowercase n is greater than 4 epsilon squared plus 12 epsilon plus 9 divided by 8 epsilon. Hence, capital N should be chosen as 4 epsilon squared plus 12 epsilon plus 9 divided by 8 epsilon. Let's prove the convergence. So capital N should be chosen as 4 epsilon squared plus 12 epsilon plus 9 divided by 8 epsilon. Limit of an as lowercase n approaches capital N is equal to the limit as n approaches capital N of 3 divided by square root of 1 plus 3 divided by n plus 1. 3 divided by n is 3 divided by 4 epsilon squared plus 12 epsilon plus 9 divided by 8 epsilon. You invert it, you flip it upside down, so you multiply 8 epsilon by 3 and the numerator becomes the denominator. So it is equal to 3 divided by square root of 1 plus 24 divided by 4 epsilon plus 12 plus 9 over epsilon. Remember that 9 over epsilon blows up to infinity because epsilon, it's like dividing by 0. So 24 divided by infinity is equal to 0 because 4 epsilon is 0, 12 doesn't count, and 9 divided by epsilon is infinity. So you end up with 3 divided by square root of 1 plus 1 equals 3 divided by 2. A new exercise, let an be equal to n plus 3 divided by n plus 7. Find the upper and lower bounds. Is it monotonic? Does an converge? Find the limit also and prove the convergence. The upper bound. A sequence an is bounded from above if there exists a number m, capital M, such that an is less than or equal to m for all values of n. For large values of n, as n increases, 3 and 7 in the numerator and the denominator respectively become insignificant or negligible. Thus, an approaches 2n divided by n, which is equal to. That would be the limit, by the way. So the upper bound is 2. Lower bound, a sequence an is bound from below if there exists a number lowercase m such that an is greater than or equal to m for all values of n. For n equal 1, a1 is equal to 5 over 9, which is approximately 0.55. That's the smallest value that you can get because as n increases from 1, an increases gradually. So an is bound from below by 5 over 9. So the lower bound or minima or infima also you can call it is 5 over 9. The upper bound suprema is 2. So as a conclusion, an is bounded in general since it is bounded from above and below. So an is between lowercase m and uppercase m, or an greater than or equal to 5 divided by 9 less than or equal to. Is it monotonic? If an plus 1 is greater than or equal to an is increasingly monotonic. If an plus 1 is less than or equal to an is decreasingly monotonic. Now without the dashed equality, an is strictly either increasingly or decreasingly monotonic. Let's check if an is monotonic. An plus 1 minus an is equal 2 times n plus 1 plus 3 divided by n plus 1 plus 7. Minus an, which is 2n plus 3 divided by n plus 7, equal 2n plus 2 plus 3, which is 2n plus 5 divided by n plus 8, minus 2n plus 3 divided by n plus 7, equal 2n plus 5 times n plus 7, minus 2n plus 3 times n plus 8 divided by n plus 8 times n plus 7. Okay, 2n squared plus 14n plus 5n plus 35 minus 2n squared minus 16n minus 3n minus 24 equal 2n squared plus 19n plus 35 minus 2n squared minus 19n minus 24 divided by n plus 8 times n plus 7. 2n squared cancel out, 19n also cancel out, so we are left with 35 minus 24 divided by n plus 8 times n plus 7. So an plus 1 minus an is equal to 11 divided by n plus 8 times n plus 7. Of course, the denominator is always positive since n is positive and 11 is positive. So an plus 1 minus an is strictly positive. Hence, an is strictly increasingly monotonic. Does an converge, and find the limit if it does? Since an is both bounded and monotonic, increasingly in this case, then it is convergent. Evaluating the limit, this is a fraction, so we will use the Hospital rule and divide both the numerator and the denominator by the variable with the highest power, which is n. So limit 2n plus 3 divided by n plus 7 as n approaches infinity. We multiply both numerator and denominator by 1 over n equal limit as n approaches infinity of 2 plus 3 over n. We divided the numerator by n over n divided by n, which is 1, plus 7 over n equal 2, because 3 divided by n and 7 divided by n approach 0 when n approach infinity. Prove the convergence. Let epsilon be greater than 0. There exists n greater than 0 such that an minus L in absolute value is less than epsilon for each n greater than or equal to capital N. An minus L in absolute value is equal to n plus 3 divided by n plus 7 minus 2 is less than epsilon, which is equal to n plus 3 minus 2n minus 14 divided by n plus 7 is less than epsilon. So 2n cancels out. We are left with minus 11, which is 3 minus 14 divided by n plus 7 is less than epsilon. So minus 11 is less than n epsilon plus 7 epsilon. We move 7 epsilon to the left, so minus 11 minus 7 epsilon is less than n epsilon. Hence, n is greater than minus 11 minus 7 epsilon divided by epsilon, which is minus 11 divided by epsilon minus 7. We choose capital N is equal to minus 11 divided by epsilon minus 7. Let's recalculate the limit based on n to demonstrate that the value of n we have chosen is correct. Limit of 2n plus 3 divided by n plus 7 as n approaches capital N is equal to multiplied by minus 11 over epsilon minus 7 plus 3 divided by minus 11 over epsilon minus 7 plus 7 equal minus 22 divided by epsilon minus 14 plus 3 divided by minus 11 over epsilon plus 0 because 7 cancels out equal minus 22 divided by epsilon minus 11 divided by minus 11 over epsilon. So limit as n approaches capital N of 2n plus 3 divided by n plus 7, we take 11 out as a common factor in both the numerator and the denominator. We are left with minus 2 divided by epsilon minus 1 over minus 1 over epsilon equal 2 plus epsilon over epsilon divided by 1 over epsilon. We multiply by minus both the numerator and the denominator. Now, epsilon is factored out, so we are left with 2 plus epsilon, and epsilon being an infinitesimally small number close to 0, so the limit is 2, which verifies the theory. Subsequences and the Bolzano-Weierstrass Theorem. Subsequences. A subsequence of a sequence an is a new sequence formed by selecting terms from an in order, but not necessarily all of them. Definition. If an is a sequence and nk is a strictly increasing sequence of natural numbers, then ank is a subsequence out of an. As an example, let an be equal to minus 1 to the power of n, then the sequence, original sequence, an is equal minus 1, 1, minus 1, 1, etc. One subsequence would be a2k, which is minus 1 to the power of 2k, which renders all the values positive. Why? Because the power is even. So a2k is equal plus 1, plus 1, plus 1, etc. Another subsequence is a2k minus 1, which renders the power odd all the times. So a2k minus 1 is equal to minus 1, minus 1, minus 1. Something to notice here is that the original sequence diverges. It means that it keeps oscillating between minus 1 and plus 1. However, the subsequences a2k and a2k minus 1 converge to a finite value. Plus 1 for a2k and minus 1 for a2k minus 1. The Bolzano-Weierstrass Theorem, or Weierstrass, the way you like to pronounce it. Every bounded sequence of real numbers has a convergent subsequence What this means is, despite the fact that the original sequence does not necessarily converge, some part of it does. As an example for that, although an equal minus 1 to the power of n diverges, which we've seen moments ago, the subsequence a to n converges to 1 because 2n makes all the powers of minus 1 to the power of 2n always even, which renders the series strictly positive at plus 1 instead of jumping back and forth between minus 1 and plus 1. Things to take note of: the limit should have a different value than that of the original sequence, especially when the latter diverges. If the original sequence converges, every subsequence converges to the same limit. In other words, if the original sequence converges, which means it has a limit, a finite one, then every subsequence, no matter what order and how many samples you take out of the original sequence, the subsequence also has to converge to the same limit value. Let an be a bounded sequence in R. This means there exists capital M greater than 0 such that an in absolute value is less than or equal to capital M for all values of n greater than 0. So the entire sequence lies within the interval minus m plus m, since an is an absolute value. We use the idea of interval bisection, dividing the interval into halves and selecting a subinterval that contains infinitely many terms. This leads us to construct a nested sequence of intervals with shrinking lengths and eventually a limit point. Since an is bounded, all an lie in a closed interval. Say an is enclosed within an interval ab, where a equal minus m and b equal plus m. Divide AB into two equal halves. The first subinterval, a plus b divided by 2. The second subinterval is a plus b divided by 2. That's the second half, starting from the middle and ending with the upper bound. At least one of these two halves must contain infinitely many terms of the sequence. Pick that half and call it I1 equal A1 B1. Now divide I1 equal A1 B1 into two halves and pick a subinterval I2 equal A2 B2, which contains also infinitely many terms. Continue this process inductively. At step k, define ik equal ak bk and pick the half interval with infinitely many terms. Each ik contains infinitely many terms of the sequence. The length of the interval bk minus ak equal b minus a divided by 2 to the power of k. It reaches 0 as k approaches infinity, so the intervals are nested and shrinking. Defining the limit point, since the intervals ik equal ak bk are closed, nested and shrinking, the intersection of all of them is a single point. So intersection k equal 1 to infinity ik is equal to L. This leads us gradually to the limit for some real number L. L is called the limit point. Construct a subsequence converging to L. We know that each interval ik contains infinitely many terms of the sequence. Choose n1 such that an1 is within I1. Then choose n2 greater than n1 such that an2 within interval 2. Continue this way for each k. Choose nk greater than nk minus 1 such that ank is within ik. This constructs a subsequence ank where each term lies in the shrinking interval ik, and ik reaches L. Therefore, limit ank as k approaches infinity is equal L. Exercise. Let xn equal minus 1 to the power of n plus 1 divided by n. Show that xn is bounded. Find two convergent subsequences of xn and what are the subsequential limits. There exists a number capital M such that xn is less than or equal to m, and there exists lowercase m number such that xn is greater than or equal to lowercase m for all values of n. When n grows very large, 1 divided by n decays quickly to 0. As for minus 1 to the power of n, keeps swapping or swinging or oscillating between minus 1 for odd n values and plus 1 for even n values. Now the maximum is at 1 plus 1 over 1, which is 2, but this is not applicable again. Why? Because in this case, minus 1 to the power of n becomes positive, plus 1 for even numbers, and the first even number that you encounter is 2. So you would have plus 1 divided by 2. So x1 is equal to 0, x2 equal 3 divided by 2, x3 equal minus 2 divided by 3, x4 equal 5 divided by 4, so it keeps decaying. x2 equals 3 divided by 2 is the highest value that you would encounter. After that, xn decreases, so xn is bounded from above by 3 over 2, or xn is less than or equal to 3 divided by 2 for all n within the natural number space. Now, for the lower bound, or xn greater than or equal to lowercase m for all values of n. When n grows very large, 1 divided by n decays quickly to 0. As for minus 1 to the power of n keeps swinging or oscillating between minus 1 for odd n values and plus 1 for even n values. Hence, xn greater than or equal to minus 1 is the lower bound for all values of n within the natural space. So xn is bounded from above by 3 divided by 2, xn is bounded from below by minus 1, hence xn is bounded in general, and xn is greater than or equal to minus 1, less than or equal to 3 divided by 2. Another important note is that xn doesn't have a limit, since 1 divided by n approaches 0 when n increases to infinity. However, at the same time, minus 1 to the power of n keeps oscillating between minus 1 and plus 1. It never settles on a definite value, on a finite limit. So the sequence diverges. Find two convergent subsequences of xn. Let n equal to k. First subsequence, x to k is equal to minus 1 to the power of 2k plus 1 divided by 2k. For k within n space, and k strictly greater than 0. It converges to plus 1 because 2k is always even, hence minus 1 to the power of 2k is plus 1 for all values of k within n. As for 1 divided by 2k, it approaches 0 for large values of k. Let n equal 2k plus 1, that would be the second subsequence. x to k plus 1 is equal to minus 1 to the power of 2k plus 1 divided by 2k plus 1. Minus 1 to the power of 2k plus 1 gives us always minus 1, because minus 1 to the power of 2k plus 1 always gives us an odd power and a negative number, because 2k itself is even, you add to it plus 1, it becomes odd. So it gives us minus 1 for all values of k strictly greater than 0 and k within n space. 2k plus 1 is an odd number. As for 1 divided by 2k plus 1 approaches 0 as k approaches a very large number, so the subsequence converges to minus 1. What are the subsequential limits? So we have x to k and x to k plus 1, both convergent out of the original sequence. Limit x to k as k approaches infinity is equal to limit k approaches infinity of minus 1 to the power of 2 times infinity plus 1 divided by 2 times infinity, which is plus 1. Limit x to k plus 1 as k approaches infinity is equal to limit of minus 1 to the power of 2 infinity plus 1 plus 1 divided by 2 infinity plus 1, which is equal minus 1. Limits exist, so both subsequences are convergent. Proving the convergence for x to k plus 1. Limit x to k plus 1 as k approaches infinity is equal to minus 1. So let's prove it. Let epsilon be greater than 0. There exists capital N greater than 0 such that x to k plus 1 minus L in absolute value, the limit happens to be minus 1, is less than epsilon for each n is greater than capital N. So minus 1 to the power of 2k plus 1, correct? Plus 1 divided by 2k plus 1, because minus minus is plus, is less than epsilon. And you know that minus 1 to the power of 2k plus 1 is equal to minus 1 in such case. For all values of n greater strictly than 0 and n belonging to the natural numbers. 1 divided by 2k plus 1, you have here minus 1 plus 1 cancels out, is less than epsilon, so 1 is less than 2k epsilon plus epsilon. 1 minus epsilon, because you move epsilon to the left, 1 minus epsilon is less than 2k epsilon. Hence, k is greater than 1 minus epsilon divided by 2 epsilon. So n is equal to 1 minus epsilon divided by 2 epsilon. This is the choice of n. Cauchy sequence or Cauchy sequence. A sequence an is called a Cauchy sequence if, for all epsilon greater than 0, there exists capital N within the natural space numbers such that an minus am is less than epsilon for all n m greater than or equal to capital N. To put it in more simple terms, as n and m approach a very large value, the subsequential terms an and am get closer and closer to each other in such a way that an minus am, the gap between these two terms, becomes so infinitesimally small, actually smaller even than epsilon, and epsilon being a number very close to 0. This is what it actually means. So as n and m increase towards very large values, an minus am, or the difference or the differential between an and am, become very small, very infinitesimal, even smaller than epsilon. A Cauchy sequence is one where the terms get arbitrarily close to each other, even if we don't yet know what they are approaching. So they must be approaching a limit. Unlike the definition of convergence, which talks about approaching a limit, a Cauchy condition talks about self-closeness of terms. Example: let an be equal to 1 divided by n. We know that limit of an as n approaches infinity is equal 0. Now for any epsilon greater than 0, choose n such that 1 divided by n, capital N, is less than epsilon divided by 2. Then, for nm greater than or equal to capital N, an minus am, an absolute value, is equal to 1 divided by lowercase n minus 1 divided by lowercase m, less than or equal to 1 divided by n less than epsilon. So an is Cauchy. We're gonna see it clearer afterwards. Exercise. Let the sequence an be defined by an equal sigma k equal 1 to n of 1 divided by k times k plus 1. Prove that an is a Cauchy sequence. You can pause the video and try to solve it first before coming back to the solution. So a sequence an is a Cauchy sequence if for all epsilon greater than 0 there exists capital N number within n such that for all mn greater than or equal to n being a very large number, an minus am, an absolute value, is less than epsilon. Cauchy sequence does not compare terms to a fixed limit. It checks if the terms of the sequence get close to each other as n, m approach infinity. This is another definition of convergence, not necessarily espoused to a fixed limit. Now 1 divided by k times k plus 1 can be broken down into 1 divided by k minus 1 divided by k plus 1. An is equal to sigma k equal 1 to n, 1 divided by k minus 1 divided by k plus 1 equal 1 minus 1 half plus 1 half minus 1 third plus 1 third minus 1 fourth, etc. plus 1 divided by n minus 1 divided by n plus 1. So all terms cancel out except 1 and minus 1 divided by n plus 1, because these terms in the middle cancel each other. Hence the sequence becomes an equal 1 minus 1 divided by n plus 1. Let's assume n greater than or equal to m, then an minus am would be less than epsilon. Okay, of course n and m greater than or equal to n. So 1 minus 1 divided by n plus 1 minus 1 minus 1 divided by n plus 1 is less than epsilon. 1 minus 1 cancel each other, so you end up with 1 divided by n plus 1 minus 1 divided by n plus 1, an absolute value is less than epsilon. So 1 divided by n plus 1 minus 1 divided by n plus 1, an absolute value is less than epsilon. N greater than or equal to m, then 1 divided by n plus 1 minus 1 divided by n plus 1 is less than or equal to 1 divided by n plus 1. Since n is greater than or equal to m, 1 divided by n plus 1 would be bigger than 1 divided by n plus 1. Hence, 1 divided by n plus 1 minus 1 divided by n plus 1 is less than or equal to 1 divided by m plus 1. To ensure an minus am is less than epsilon, we should choose m greater than or equal to n, where 1 divided by n plus 1 would be less than epsilon, and n would be greater than 1 divided by epsilon minus 1. The completeness of R. The real number system R is complete, meaning every Cauchy sequence in R converges to a limit in R. If an is a Cauchy sequence in R, then there exists L within R such that limit of an as n approaches infinity is equal to L. So the Cauchy sequence, in other words, would have a limit. Let an be a Cauchy sequence in R, proving it is bounded because an is Cauchy for some n and for all nm greater than or equal to n. an minus am in absolute value is less than 1, then an is less than or equal to an capital N plus 1. So the sequence is bounded. Use Bolzano-Weierstrass. Since an is bounded by the Bolzano-Weierstrass theorem, it has a convergent subsequence. So an approaches L within R. Now to better clarify this line here, this means that as n becomes much larger, an has an upper bound an plus 1. So an for all other values of n remain less than or equal to an plus 1. In other words, it has an upper limit. Show the entire sequence converges to the same limit. Since an is Cauchy and a subsequence converges to L, we can show that the whole sequence also converges to L. Let epsilon be greater than 0 since an is Cauchy. There exists n1 such that for all nm greater than or equal to n1, an minus am in absolute value is less than epsilon divided by 2. Since ank approaches L, there exists k such that nk is greater than or equal to n1 and ank minus L, so that would be half of the sequence, less than epsilon divided by 2. Now for any n greater than or equal to n1, an minus L in absolute value is less than or equal to an minus ank plus ank minus L is less than epsilon divided by 2 plus epsilon divided by 2, which is epsilon. So simply, we divided the sequence into two sets, okay? The sum of these two sets approach epsilon. One half of the set would approach then epsilon over 2, half of the approximation. So an tends to L and thus the entire sequence converges. Prove the following sequence an is a Cauchy sequence. An equal n divided by n plus 1. So for all epsilon greater than 0, there exists n within n such that mn greater than or equal to n, an minus am in absolute value is less than epsilon. An can be rewritten as 1 minus 1 divided by n plus 1. So an minus am is equal to 1 minus 1 divided by n plus 1 minus 1 minus 1 divided by n plus 1 in absolute value is less than epsilon. 1 and 1 here cancel out, so we are left with 1 divided by n plus 1, it is positive, minus 1 divided by n plus 1, less than epsilon. So n plus 1 minus m minus 1 divided by n plus 1 times n plus 1 is less than epsilon. N minus m in absolute value divided by n plus 1 times n plus 1 is less than epsilon. We choose n greater than or equal to m so that n in absolute value minus m in absolute value is less than or equal to m less than or equal to capital N. As for n plus 1 times n plus 1 would be then less than or equal to n plus 1 squared. So n divided by n plus 1 square is less than epsilon. N divided by n square plus 2n plus 1 less than epsilon. Hence, n is less than n square epsilon plus 2n epsilon plus epsilon. So n is less than n square epsilon plus 2n epsilon plus epsilon. You move the right side to the left, so n minus n square epsilon minus 2n epsilon minus epsilon is less than 0, minus n square epsilon plus n times 1 minus 2 epsilon minus epsilon is less than 0. You multiply by minus, so n square epsilon plus 2 epsilon minus 1 n plus epsilon is greater than 0. When we multiply by minus, we need to flip the inequality. This is a quadratic polynomial equation that we need to solve using delta, the discriminant, and finding the roots. So delta is equal to epsilon minus 1 squared minus 4 times epsilon, which is minus 4 epsilon squared, which is equal to minus 4 epsilon plus 1. N1 is equal to minus 2 epsilon minus 1, which is b, minus square root of delta, divided by 2 epsilon, N2 equal minus b also, which is 2 epsilon minus 1, the part multiplying n, plus square root of delta divided by 2a, a being the part multiplying n squared. Let an equal square root of n squared plus 1 minus n. Prove that the sequence an is a Cauchy sequence. But let's start with whether it is convergent, whether it's a Cauchy sequence after that, whether it's bounded, and if it has a limit. So an can be written in a different way. We multiply by the conjugate, both numerator and denominator. So square root of n squared plus 1 minus n is equal to square root n squared plus 1 minus n times square root of n squared plus 1 plus n, up and down, numerator and denominator, equal n squared minus n squared plus 1, which is 1 divided by square root of n squared plus 1 plus n. Because n squared cancels out. Negative n squared cancels out with plus n squared. So an can be factored out even deeper than that. It is equal to 1 divided by n squared can be taken as a common factor in the denominator within the square root. You multiply the inside of the square root by n squared, which gives you n squared times 1 plus 1 divided by n squared. You take it to the outside, it becomes n times square root of 1 plus 1 divided by n squared plus n. So n is a common factor for the denominator, which is n times square root of 1 plus 1 divided by n squared plus 1. So the limit of an as n approaches infinity is limit of 1 divided by n times square root of 1 plus 1 divided by n squared plus 1. As for 1 divided by n squared, it decays very quickly given that it is a squared value. So what we end up with is 1 divided by infinity multiplied by square root of 1 plus 1, which is 1 divided by 2 times infinity equal 0. The limit exists and is finite, so the sequence is convergent. An is equal to 1 divided by square root of n squared plus 1 plus n. Am equal 1 divided by square root of m squared plus 1 plus n. Let's check an minus am. Going back to the original form that we found, 1 divided by n times square root of 1 plus 1 divided by n squared plus 1 minus 1 divided by m times square root of 1 plus 1 divided by m squared plus 1 is less than epsilon. Let's choose m greater than n greater than or equal to n, and n is very large. So 1 divided by n squared approaches 0, 1 divided by m squared approaches 0 as well. Since we've gotten rid of 1 divided by n squared and 1 divided by m squared, we are left with 1 divided by 2n minus 1 divided by 2m is less than epsilon. This is true given that m is greater than or equal to n. So 2 times m minus n divided by 4mn is less than epsilon, or 1/2 times absolute value of m minus n divided by mn less than epsilon. M in absolute value minus n is less than or equal to n, since m is greater than n. So m is greater than or equal to n, mn is less than or equal to n squared. Hence, n divided by n squared is less than epsilon, 1 over 2n less than epsilon, so n is greater than 1 divided by 2 epsilon. We simply switched between n and epsilon. Let's recalculate the limit based on this value for n. So limit an as n approaches capital N is equal to 1 divided by, instead of n you place 1 divided by 2 epsilon times square root of 1 plus 4 epsilon squared. Why? Because 1 divided by n squared is 1 divided by 1 over 2 epsilon squared. which is 4 epsilon square. So you flip it back into the numerator and you get 4 epsilon square plus 1. Now epsilon is very close to 0. It is an infinitesimal number that is very small, very tiny. On the other hand, 1 divided by 2 epsilon approaches infinity because epsilon is very close to 0. Meanwhile, 4 epsilon square is equal to 0 because epsilon is very small, very close to 0. So square root of 1 plus 4 epsilon square plus 1 is equal to, so limit an as n approach capital N is equal to 1 divided by infinity, which is 1 over 2 epsilon, multiplied by square root of 1 plus 4 times 0 plus 1, which is 1 divided by 2 times infinity equals 0. So we proved the limit using this method. Let's check whether an is bounded. For n equal 1, a1 is equal to 1 square root of 2 plus 1. For n equal 2, a2 equal 1 divided by square root of 5 plus 2. So it is decaying, it is descending. Let n greater than 0 be the upper bound. An is less than or equal to m for all n within n, the natural space, and n strictly greater than 0. As n increases, an decays gradually to 0 by the growth of the denominator. Hence, the upper bound is 1 divided by square root of 2 plus 1. So an is less than or equal to 1 over square root of 2 plus 1 for all values of n within n space. Let's check the lower bound. There exists m greater than 0 such that an is greater than or equal to lowercase m for all values of n. Now the limit of an as n approaches infinity is equal to 0. This is as low as you can get, so 0 is the lower bound. An is bounded from above by 1 over square root of 2 plus 1, and from below by 0, hence an is bounded in general, which means an is greater than or equal to 0, less than or equal to 1 over square root 2 plus 1. Let's check the limit. So we've already seen the limit. An is equal to 1 divided by square root of n squared plus 1 plus n. We've taken n to the outside. The inside had cancelled out, so the limit is equal to 0. An is a Cauchy sequence and has a limit in R. As a conclusion, it is complete in R, because not only the terms themselves approach each other for large values of n, but also they approach a finite and definite limit. Thank you so much for watching and see you next time.